Welcome to the deep dive. You know, when you think about modern factories, all that automation,
Wow.
robots, sensors, everything working together, it's like this incredibly complex dance. And managing that dance, making it modular, resilient, maybe even surprisingly simple, well, that's where some often unseen components come in. Today, we're pulling back the curtain on one of these unsung heroes, the ESWIT TCH function block. Now, this isn't just some random bit of code. It's a standard element within the IEC 61499 norm, and it's specifically designed for managing switching operations in industrial automation. We've been looking through the technical docs and AI overview too, and what really jumped out was the sheer power you get from its basic logic. Seems almost too simple. So our mission today is to unpack what it does, how it does it, see where it's used in the real world, and really grasp why it's so fundamental. Let's get into it.
Absolutely. And, to really get the E-switch, we kind of have to take a step back first. Look at the bigger picture, which is the IEC 61499 standard itself. This isn't just any standard. It's the global norm for function block architecture in industrial control systems. Measurement, control, the whole lot.
Right, the foundation.
Exactly. It gives us this common language, this framework for building control systems in a modular way. Distributed control, too. And function blocks, like our eSwitch, are the crucial building blocks within that framework. Think of them like reusable software components. If you know object-oriented programming, it's a bit like that self-contained bits of logic.
Okay, so eSwitch fits into that standard. It's specifically called an event function block. What does that event part tell us?
Ah, good question. That signals its core behavior. It doesn't continuously process data like some other blocks might. Instead, it reacts to specific events, things happening at discrete moments in time.
Gotcha. It's event driven.
Precisely. And its main job, conditional event routing. Basically, it looks at a control signal and decides, based on that signal state, where to send an incoming event. It's like a little traffic director for events.
A traffic director, I like that. So let's look under the hood. What are its parts? The inputs. There's EI, right? The event input, that's where the event, whatever it is, arrives.
Correct. That's the trigger.
And then there's G, the generic input, or the criterion, as some docs call it. The criterion, this is the key, isn't it? This is the control signal that makes the decision.
That's the one. Its state, typically 0 or 1, determines the path the event takes. Each state represents a condition the system cares about.
Okay, input's clear. EI brings the event. G decides where it goes. What about the outputs? Where can it go? Typically, we see EO0 and EO1, right? Event output 0 and event output 1.
That's the standard setup, the two primary destinations for the event.
I saw one source call them ZWIJ branches. That makes sense visually, like the event hits a fork in the road.
Yeah, it's a good way to think about it. Different branches leading to different actions or functions. And what's neat is how simple this structure is, yet how effective it is for making decisions. And you mentioned the standard setup, but it's worth noting, sometimes you might see variations or ways to handle situations where neither condition is met, like an else case, a default path,
Aha, okay. A default route.
or even using multiple criteria together, combining blocks maybe for more complex switching. But the core is this simple, powerful binary switch.
So let's trace the logic. An event hits EI. What happens next?
Okay, so the block immediately checks the state of the G input, that criterion signal.
And if G is 0?
If G is 0, the event that came in on EI gets sent out through EO0. Event output 0 fires.
And EO1?
EO1 stays quiet, inactive.
Okay, simple enough. And the flip side, if G is 1,
Then the opposite happens. The event gets routed to EO1, event output 1 fires, and EO0 remains inactive.
so it's a clean switch, either here or there, based entirely on G.
Exactly. It's that fundamental conditional routing. And that simplicity is what makes it so powerful and versatile. You can use it for all sorts of control flow decisions within a system.
Right. It's not tied to what the event is, just whether the condition G is met.
Precisely. It can be switching between operating modes, handling errors differently, directing tasks, all based on that simple check. It's a big step up from older ways where logic like this might be buried deep in complex code. Much clearer, much more modular.
Okay, theory makes sense. Let's talk real world. Where would I actually see an eSwitch doing its job? Give us some examples.
Sure. A classic one's operating mode control. Imagine a machine or a whole plant section.
Okay.
You can use an eSwitch to switch between, say, manual mode and automatic mode. Maybe G0 means manual. So any relevant operational events get routed via EO0 to the manual control logic.
And G1 would be automatic.
Right. G1, events go at EO1 to the automatic sequence controller. It provides a really clear, defined switch point between those modes.
That's pretty neat. What else?
Error handling is another big one. You often need to treat errors differently based on severity.
Makes sense. Critical versus non-critical.
Exactly. So you could set it up so if G0, it's a non-critical error, maybe log it or display a warning via EO0. But if G1, that indicates a critical error.
And that event goes to EO1.
Yep. Triggering maybe an immediate shutdown sequence or alerting an operator urgently. It allows you to separate and prioritize responses effectively.
I can see that being incredibly useful. Any others?
Well, think about distributed systems. Systems spread out over multiple controllers or devices.
Uh-huh.
An eSwitch could be used to dynamically route events or tasks to different controllers based on, say, system load or configuration.
Mm-hmm.
G might represent which controller is currently best suited for a task.
So it helps manage communication and workload in those bigger spread out systems.
Precisely. It directs the flow of information or commands to the right place at the right time, adapting as needed.
Wow. Okay. So from mode control to error handling to distributed logic, it really pops up everywhere.
It does. And all these examples really highlight the benefits we talked about earlier: modularity, clarity, efficiency. You're using this one simple standard block to handle quite different control problems reliably. It avoids reinventing the wheel.
It's that industrial elegance you mentioned. Okay,
Yeah.
so summing it up, what are the core advantages? Why is this block so valued? We've touched on them, but let's list them out. First, simplicity, right? It's easy to grasp, easy to use.
Definitely. Low barrier to entry for engineers.
Second, flexibility. It works for any kind of event in all sorts of contexts: mode switching, errors, data routing.
Yeah, it's agnostic to the event type, which is powerful.
And third, crucially, reusability, because it's part of the IEC 61499 standard.
You can just drop it into different projects, different applications, knowing it will behave predictably. That speeds up development massively.
So it's more than just a technical component then.
Oh, absolutely.
Yeah.
I mean, you can see the eSwitch H as sort of a symbol for the whole philosophy behind IEC 61499. Well, that philosophy is all about modularity, making things reusable, driving efficiency in how we build automation systems. The eSwitch embodies that. It's a simple, standard building block that lets engineers construct really complex, reliable systems more easily and quickly. It's a tool that directly helps manage complexity in our increasingly automated world.
A small block with a big impact on the design process itself.
You got it. It simplifies things at a fundamental level.
Right. Well, that brings us towards the end of this deep dive on the eSwitch. It really is a fantastic example of elegant simplicity tackling complex problems. Despite being so basic, it's clearly fundamental, indispensable even, in modern industrial automation. It just perfectly captures that power of modular, reusable design, a testament to how well-designed standard components let complex systems run smoothly.
Absolutely. It's a cornerstone. So as we wrap up, maybe something for you, the listener, to think about. Consider this principle: using simple standardized switches to manage complex flows. We see it here in automation, but where else does this apply? Think about decision pathways in software, maybe data routing on the internet, or even just, processes in daily life. How often do we rely on these hidden, simple, conditional mechanisms to make complex things work?
That's a great thought. What other intricate systems out there might be running on similarly elegant, simple solutions we just don't see? Something to mull over.